What really makes the DFT interesting is not only that it is computationally feasible, in that it doesn't involve an infinite sum or something like that, but it can also be performed very efficiently. And so the fast Fourier transform, or FFT, is an algorithm for calculating the DFT. In order to develop this, we're going to take a little bit of development, and we're going to change our notation back to that W notation that I said I didn't prefer. And the reason why is because we're going to be writing a lot of essentially e to the negative j 2 pi k over n times n, and it'll just get messy. So before we start, let's put up a few things just as reference. First is the x of k, as we know, is equal to the sum over 0 to n minus 1 of x of n. And using our notation, that's w of n raised to the power kn. And that's for k is equal to 0 through n minus 1. First observation is, if we were to directly compute this, that requires, let's see, we want to compute our whole DFT, so we'll evaluate this for capital N different values of k, and each one of those is a sum of n products. So that's going to be n squared complex multiplies. So just as a reference. One other thing that we'd like to point out is, remember that Wn is equal to e negative j 2 pi over n. So Wn squared is equal to e to the negative j 2 pi times 2 over n, which is also equal to e to the negative j 2 pi over capital N divided by 2. Just throw that 2 down in the denominator of the denominator, which is equal to Wn over 2. So we'll use this property coming up pretty soon. All right, time to jump in and develop our fast Fourier transform. We're going to start by splitting x of k into two sums. And we will have the sum over n even of x n w n, oops, little nk, and the odd ones. The ranges remain the same, but we'll just, for ease, just know that we're going from 0 to capital N minus 1. We do this. So how do we index this? Well, in two ways. For n odd, we can just range over r, where n is equal to 2r. And for its odd, we can say n is equal to 2r plus 1. So that'll give us the odd samples. And using this new notation, we can write the sum from r equals 0 to n over 2 minus 1, x 2r, wn 2r k. And we get something similar for this other side. we go over the same range now. R equals 0 to capital N over 2. But to get the odd samples, we do 2R plus 1. And the same here, we have 2R plus 1 in place of N, and then K. So now we're back to the same sum, but we're actually not going to combine them quite yet. We're going to do a few other things that are kind of clever. At least I think they're kind of clever. I can say that because it wasn't me that thought of it, so it's not boasting. This gives us x 2r, and now this would be w n squared to the rk. We'll have something similar here, 0 n over 2 minus 1 x 2r plus 1. Now we have, actually we're going to give myself a little more room, so we can do this all in one step. We'll once again have our wn squared rk, but we also have this plus 1 multiplying by k. Since k is not dependent on r, that just comes out front as wn to the k. Well, we have this beautiful property that we found up above, that w squared is equal to w sub n over 2. So, finally, we can write this as the sum of r equals 0, n over 2 minus 1, x 2r, w, n over 2, rk, plus wnk times the sum over r from 0 to n over 2 minus 1, x 2r plus 1, wn over 2, rk. Well, this is just a DFT of length n over 2. And this is also a DFT of length n over 2. But, of course, we have that factor out front. So, nothing magical, but we did take a DFT of length n, and we turned it into two DFTs of length n over 2. So, if we were to calculate the entirety, as in for all k, the FFT or the DFT of length n over 2, it's going to take us k multiplies. I'm sorry, n over 2 multiplies. And so we have suddenly gone from, we're calculating for n values, or yes, calculating for n values of k, but each one is based on 2 half-length DFTs. So to calculate all n over 2 values of our first DFT, And all n over 2 values of the second DFT is going to be n over 2 squared. Then we have this additional multiplied by w to k of n, and then we have to sum them all up. So total computation in terms of multiplies is n over 2 squared multiplies plus n over 2 squared multiplies plus n multiplies for w to the k of n. That's not bad at all. So that's going to be n squared over 2 plus n. And that is, in general, less than n squared for most values. So let's say n is equal to 2. That's going to be 2 plus 2 is equal. But if n is equal to 4, we would have 4 squared is 16, divided by 2 is 8, plus 4 is 12, which is less than 4 squared, which is 16. So that works. Strictly less than for n is greater than 2. So let's see what this looks like graphically. This is the beginning of the famous butterfly diagram. The reason it's called that is because this shape appears over and over, and if it just had a body and antennas and a pretty little design on it, it would be a butterfly. It doesn't have those, but our imagination can carry us there anyway. Okay, so up here, we took the even samples of x. And down here, we take the odd samples of x. We do an n over 2 point DFT on each set of those, and we get our two outputs. Now remember, we had to add the outputs together. So I guess I'll leave that highlighted. Let's go down and look at each of these. So each output is going to be the sum of a term from our n over 2, or our even sample DFT, and our odd sample DFT. So let's take this one, for example. This is equal to the output from the even sample DSP, or DFT, and we take the odd sample. We multiply the odd sample by w squared of n, or w sub n squared. And we note that the square there is shows up in those two places. So k is 2, and that's where the square comes from. Similarly, to get, say, x of 7, we would take this last output from the even DFT and the last one from the odd DFT, and we add in, or we multiply the odd one by w sub n to the 7th, giving us our output as described there. So this is a way of graphically describing what goes on. You could trace all of those out and see that it all works. So once we've done this, then that worked so well the first time. Why don't we take our n over 2 point DFTs and divide them further. If an n point DFT can be computed with 2 n over 2 points, then maybe an n over 2 can be computed with 2 n over 4 points, and sure enough, it can, and that's not really hard to see that this right here is our n over 2 point DFT from over there on the left. And we can continue doing this till we get down to a 2 point DFT, which is trivial, as we'll see. So now that we have this kind of cool structure going, let's actually carry that one step further. And in this particular case, we have n is equal to 8, so n over 4 is 2. So let's go ahead and stick in that 2 point DFT and see what it looks like. Okay, a few things about computation. As I mentioned, you would rather have n is equal to some power of 2, so we can do this DFT. And so what I've shown here is the number of megaflops used by MATLAB, or million floating point operations, used by MATLAB in the FFT function. It used to be, many years ago, that you could have MATLAB tell you exactly how many flops it used. And this was great for making plots like this. They've since changed their underlying mathematics engines, and they don't keep track of that because it burns cycles to keep track of how many cycles you're doing. And so to make it more efficient, they've taken that out. So this type of available data is not available in the most recent versions of MATLAB, but it is in very old ones. So here we have 256, length n, 128, 64, 32, 16, 8, 4, 2, 1. And the number of operations it takes, you can see, is very, very slight. If, on the other hand, you have maybe powers of 3, what can be done? Well, you can actually divide things up. Say if you had powers of 3, you could divide it up into FFTs with not the odd and the even, but rather the 3 sums, each with a multiple of 3, multiple of 3 plus 1, and multiple of 3 plus 2, and come up with an efficient architecture. Is it as efficient? No, it's not, but it's still pretty efficient. So as long as you can break down your DFT into smaller DFTs such that it divides evenly into n, you're okay. If, on the other hand, you can't, it's because you have a n is prime. And if n is prime, it follows this n squared curve for computational order n squared computations. And here it's order n log n computations. And then in between, depending on what prime factors you have, there are various algorithms that apply that give you some efficiency, just not as much as the n log n. So let me add in here another important consideration. These values, the w's that are multiplied in various places around here, are called twiddle factors. Second, each of these butterflies is kind of interesting in that it takes 2 values, and it was drawn this way very intentionally. It operates on those 2 values, and then it stores them back in the same location. So this is computation in place. This is very nice from a memory access point of view. When you're doing an endpoint DFT or FFT, you only need that endpoint buffer. You don't have to allocate extra buffers to do things in. Obviously, you'll have maybe some temporary registers that are used in computing values. But once you've computed those values, you store them right back where they came from. And then you index things differently. Something else to notice is that each one of these butterflies basically will have a -1 on the bottom chain I would like next to call your attention to the values over here on the left. So we have obviously the even ones at the top and the odd ones at the bottom. But then we have, we did that in the first stage. In the second stage, from the even ones, we re-indexed them, 0, 1, 2, 3, and we took the even ones of those and put those on the top and the odd ones on the bottom. And this continues. And when we're all done, notice they're not in order anymore. It's kind of messed up. So here we have 0, 4, 2, 6, 1, 5, 3, 7. Well, interestingly, if you take these values and we just put them in a different form, 0, 4, 2, 6, 1, 5, 3, 7, we can write these in binary. Like this. We can see that if we were to read these, reverse the bits, we would get 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Oops, 1, 1, 1. We can see that when we reverse the bits, it counts up normally. So this is called bit reversed addressing. And also, since the DFT and the FFT are so important, many DSP chips actually have a special addressing mode built in that is bit reversed addressing. And so what you do is you say load your index register with the number, whatever output you want to access, or the order you want to access it. You access it in the bit reverse mode, and it finds that value in the table. So for example, if you wanted to access the 0th one, no big deal. If you want to access the next value, you would load a value of 1, and it would return an address of 4 and grab x of 4 for you. So kind of a cool feature. Another thing about the FFT, this is kind of FFT information moment here, is we did what is called the decimation in time FFT. So for it to have a name like that, you might guess that there is another FFT you could use, and sure enough, it's called the decimation in frequency FFT. So the decimation in frequency FFT gives you a butterfly plot that essentially looks like this one if you mirrored it, if you flipped it around. Finally, if we I guess we'll pull up another page. There's another form of the FFT where we change things around a little bit, how we factor values. So it doesn't take too much effort to see that we could refactor our butterfly that we had on the previous page that's on the left to look like one on the right. So why is that? Well, it might be a little hard to see just straight up. The W sub n of 4, this is 4, and these values are 4, n is equal to 8. It's going to give us a -1, as we saw before. But I think the rest is easiest if we follow through, because this is factored over the whole thing, and see what goes on. So x of n, x of 0 is going to be, capital X of 0, the DTFT of 0, is going to be the sum of every component, every input in there. And so let's see how that works. We get that contributing, and we get that contributing. How does this one get there? Oh yes, this one gets there this way. That is summed in there that way. x5 joins in there, x3, and finally x7. So every value is added in, and the only thing they're multiplied by is Wn of 0. So that works. Wn of n, or sub n to the 0, is of course 1. So we've added them all up. Okay, let's try one of these others. x3. What has x3 got to have? x3, capital X3, is going to be equal to xn plus, and we're going to have, I don't need n, that's a 1, or 0, x0 plus x1 of e to the negative j. Actually, let's put it in terms of w's, we have it there anyway. Wn1 plus x2 Wn2 plus x3 Wn3 plus x4, you get the idea, Wn4, and so on. This is just from our definition of the DFT. And, oh, I'm sorry, I forgot, 3 times 3 times 3 times 3 times 3. Okay, so let's follow this through. This is going to be a little bit more complicated. So we're going to have to figure out how x of 0 contributes. X of 0 will follow this chain down, and it's not multiplied by anything. Good. Check. Let's go x1. x1 is over here, and it needs to be multiplied by w3. So where does it actually get added in to x3? It's going to have to come from this lower chain. So it'll go here to here, there to there, here. Oh good, it's multiplied by w3. Check. Now we have x2. x2 is up here on the upper part, and it's going to have to be multiplied by wn to the 6th power. Let's see. We come in here, down there. Good, we multiplied by wn squared. Now if we could just multiply it again by wn to the fourth, and there it is. The negative 1 is wn to the fourth. And so we have that one. And you can see we can do this for a little while. Let's do one more. And then I'm going to be running out of colors, so we'll stop. So wn to the ninth multiplied by little x of 3. So that's down, x of 3 is down here. What path are we going to follow? It's going to have to come here. Follow this lower chain. We get a 2. Now that's good. Then we get a 4. Okay, so now we're at 6. Then we get a 3. Now we're at 9. So that checked out as well. Now eventually we're going to get to the point where we're looking for, say, 7 times 3, 21. And it's easy to see that as you follow this chain through, you're never going to add things up to get to a 21. But w sub 8 to the 21 is the same as w sub 8 to the 21 minus 8, or 21 minus 16, so wn to the 5. And so as you go through, this is just a clever refactoring that reduces the number of multiplies. So why does it reduce the number of multiplies? Well, we have a lot of trivial ones in here. That's trivial, 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 so on and so forth. In this case, that's trivial, and that's trivial, as we saw before, because those are just j terms, negative j terms. And so the only non-trivial ones we're left with are those two. But this format allows us to essentially replicate our structure many times. This is nice, easy to tile multiplication structure. So the FFT has been studied tremendously, and we've just kind of hit the surface of it, but there are some really efficient algorithms. In fact, it comes down to now algorithms for the FFT. Since it's so efficient, people of course want to make it more efficient. There's one called the FFTW. It's short for the fastest Fourier transform in the West. And this one takes a lot of different algorithms, and it first profiles your particular architecture, how it accesses memory, things like that, and then it selects different code sets based on your particular architecture, and ends up to be extremely fast. But you shouldn't have to worry about that. You can find FFT code in C, and then in almost any other language you have it as a library. MATLAB, Python, whatever you might be working with.